My name is Eva Bezak. I'm the Vice President of the International Organization for Medical Physics, and I am the moderator of today's webinar. I welcome all of you in this particular presentation that is second in the series of lectures that we provide to celebrate the International Medical Physics Week. And today we are really fortunate to have Dr. Brian Gonzales from Seattle with us, who will be talking on micro-X carbon nanotube emitters, X-ray tubes, and unique imaging applications. Dr. Gonzales is a chief scientist and CEO of Micro-X Inc. in the United States. He has a Ph.D. in biomedical engineering from University of North Carolina and has published multiple peer-reviewed scientific journals focused on X-ray computed tomography using carbon nanotubes X-ray technology. He has been assisting in the transition of these technologies to full commercialization, and is in partnership with Micro-X with Flinders University and the University of Melbourne here in Australia, where I am located. Dr. Gonzales will now deliver his talk. You will be all the participants muted and your videos will be turned off to save the bandwidth. You are though encouraged to type your questions into the Q&A tab in your Zoom screens, and following Dr. Gonzales's presentations, I will read your questions and we will run a Q&A session. This particular presentation will attract one continuous education point, and the certificates will be delivered, sent to you via your registration email tomorrow. Over to you, Brian. Thank you.
Thank you very much, and thank you for that introduction. Hello, everyone. Thank you for giving me the opportunity to talk to you today and to tell you about what we are doing at Micro-X with our carbon nanotube emitters, how we're turning those into X-ray tubes, and the unique imaging applications of them. Just by way of introduction, Micro-X is a technology company based in Adelaide, South Australia, and Seattle, Washington, United States. We have approximately 100 employees. More than half of them are engineers or scientists. We collaborate with a number of universities, as mentioned, including Flinders University and University of South Australia in Adelaide, Melbourne University and Monash University in Melbourne, Australia, and Johns Hopkins in the United States. We are the first company to commercialize carbon nanotube X-ray sources specifically for medical imaging applications. Some people have done carbon nanotubes for other applications, such as dental or kind of low end, but we're the first with a high current carbon nanotube X-ray source. So today I'm going to start by introducing carbon nanotube electron emitters in general, and then talk about what makes Micro-X's CNT emitter unique, how that allows us to make unique X-ray tubes, and the imaging systems that we are making with those unique carbon nanotube X-ray sources. So by way of introduction, to make an X-ray, you need an electron current. And electrons in a vacuum, when they're in a metal at rest in a vacuum, there's a barrier. That barrier prevents the electrons from escaping into the vacuum. So typically, electrons are given energy through thermionic emission. Heat energy is input into those electrons that allow them to move over that barrier and create a current. That current is then used to make X-rays by accelerating it in a potential in a vacuum. Other ways of inducing an electron current is photoemission or Schottky emission. Schottky emission is interesting because it's similar to thermionic emission, only it uses an electric field as well to push down that barrier. But all of those methods require inputting some external energy into the conductor that the electrons are sitting in. Field emission is a little different. In field emission, electrons that are at rest in that conductor can tunnel through the barrier, with some probabilistic amount. And so you can get a small to non-existent current at normal, but as you push down that barrier with an increasingly strong electric field, more and more electrons tunnel through that barrier in field emission. So what you need to make field emission work is you need a very, very high local electric field at the conductor to begin pulling more and more electrons out. Because of that, field emission, there's been significant amounts of research done to create field emission devices. So these are devices specifically designed to have a high aspect ratio. What that means is that they have a very, very sharp point and are as long and narrow as possible, because the sharper the point, the sharper or the greater the electric field is at that point, and the higher the current, the electron current coming out of that point is. So here you will see in this image a number of different devices that have been investigated for field emission, using micromachining, nanomachining, or plasma devices to create them. They all exist at the very, very small nanoscopic and microscopic scale. And depending on the size, they give different amounts of current, depending on the material and the size. Carbon nanotubes were identified almost 30 years ago as a near ideal field emission device. And the reason for that is carbon nanotubes have a very, very, very high aspect ratio. A carbon nanotube is a sheet of graphene. Imagine a two-dimensional diamond, a graphene structure, which is just a hexagonal carbon structure, as a two-dimensional sheet that's been rolled up and made into a tube. A carbon nanotube, because of that, has a very, very, very high aspect ratio. It's nanometers wide and microns long. So it's very sharp, very pointy. And when carbon nanotubes are just one or a few layers of graphene, they act as a conductor. So they're nearly as conductive as copper, which means that they are an ideal field emission device. You can get up to microamps of current from a single carbon nanotube. And they're very, very structurally stable because they're graphene, which is one of the most, if not the most structurally stable material that we know about. However, to get from microamps to the milliamps of current that you would want for medical imaging application, you have to take the individual carbon nanotube and replicate that into a large area. So here you will see what that looks like. So if you have a single carbon nanotube, you can see in this image how the electric field is bunched together at the point. That bunching together is what creates that field strength. The field strength is what pulls the electrons out of that carbon nanotube in field emission. When you put multiple carbon nanotubes close together, the field becomes less bunched together. They shield each other. The electric field no longer is as consolidated. So you need a higher electric field to get the same current. So the challenge with scaling carbon nanotube field emission is, how do you balance lots of carbon nanotubes as close together, but not so close together that you don't get good field emission from each device. So this is an image of trying to grow carbon nanotubes relatively close together so that you get a high current density, but appropriately spaced so that you don't shield one another. And this can be quite challenging to do. And you might recall from the earlier image, other field emission devices try to do the same thing, where you take some device, it might be like a moly tip or a silicon tip, and you try to space them evenly so that you get the maximum field emission at the tip, but you get the maximum number of devices in an area. And this can be quite challenging to do, because the precision involved is quite hard to get as this scales, to get the same device over larger and larger areas. in addition to that, there's a couple of other challenges to conventional carbon nanotubes. An individual carbon nanotube will burn itself out if you put too much current. The field emission device is so efficient that it doesn't ever stop. It just keeps delivering more and more current as you increase the field at the tip. So this is an image where there's a single carbon nanotube, there's a voltage applied, and as that voltage increases, the current increases and increases until suddenly it stops. And the reason it suddenly stops is the carbon nanotube has been destroyed. The mechanism for destruction is that the current flowing through that carbon nanotube is so high that it begins to generate heat into the carbon nanotube. And that heat has only one place to move, and that's to the tip of the carbon nanotube, where it begins to actually thermally emit and burn away the carbon. So you'll very quickly burn itself out if you put too much current. If you keep below that limit, the carbon nanotube will just continuously emit. There's not another way for it to destroy itself when it's emitting stably. It's just if it goes to overcurrent. However, if you try to put multiple carbon nanotubes and you try to draw the same current from each of those systems, what you end up doing is you end up overdriving the slightly more efficient carbon nanotubes. And if you look at the consistency of carbon nanotubes in a large area, there's always some variation both in diameter and in height. And that variation means that some of those individual carbon nanotubes are more efficient than others. The more efficient ones in the presence of a uniform electric field will turn on harder than their neighbors. And that current has a tendency to burn out the efficient ones. And so the efficient ones burn out, and then the less efficient ones are overworked. So very quickly in a large area emitter, you can burn out all of the carbon nanotubes and destroy the entire emitter. And this has been a fundamental challenge to field emission devices. People have been very excited about what could be done with field emission devices, cold cathodes for X-ray tubes for a long time, but it's been challenging to scale that CNT emitter array so that you get enough current without burning out the emitter and in a way that is repeatable and cost effective. What Micro-X has done is we have a unique way where we've been able to scale the small emitter and scale it so that we can get very high current. We can actually get up to 200 milliamps stably and consistently over an emission area, a large area emission area with about 75 square millimeters. So here in this image, you will see the process that we have experimented with different sized emitters. So we can actually create an emitter as small as 1 millimeter squared, as big as 100 millimeters squared, and we can vary how much current and how much life we get out of that CNT emitter. And it's the same process. And so that means that our process is very scalable and very consistent across it. And what makes our process unique is it's based on two physical properties of the bonding material that bonds the carbon nanotubes to the matrix. And I'm going to discuss what those two properties are that makes our CNT emitters unique. So this is an actual scanning electron microscope image of our CNT emitters. And you will notice that it looks very different than the previous images. What you don't see is the consistent uniform CNT emitter stacked together like a regimented soldiers. Instead, you see this amorphous mixture and CNTs randomly coming off of it. So at the very smallest level, you'll see a couple of very small CNTs, few walled CNTs bonded. And then as you zoom out, you see what the emitter looks like at further and further scale. And what the unique part of our process is what's inside this material, this amorphous material that bonds these carbon nanotubes to a metal substrate. And it has two properties to it. The first property of that material is that it's highly resistive. And it's highly resistive in such a way that it has multiple resistive pathways. So what this means is, the way I like to describe this is, think of an individual carbon nanotube like a channel of water. And it's a tiny little channel of water that you would run a little stream through. And behind those little channels of water, you've got a big rushing river. And if you were to take that big rushing river and push it through that little channel of water, it would just wash it out. But if you took that big channel of water, that big rushing river, and you broke it into 2 rivers, and then you broke those 2 rivers into 4 rivers, and then you broke those 4 rivers into 16 rivers, and further, it would inevitably get to where it could evenly spread through hundreds of small little streams, the same amount of water that was coming out of that rushing river by breaking it down in steps. And that's what this resistive matrix does, is it takes this huge amount of current coming out of a substrate, a metal substrate, a solid metal block, and it spreads it out evenly over that large area so that by the time it gets to each individual CNT emitter, there's only a certain amount of current that can flow through that individual CNT emitter so that the individual CNT emitter never burns out and evenly spreads the current over our entire large area emitter. So what you see here is a couple of tests that we did where we varied the resistivity and the resistive pathways in materials. So as you increase the if there's no resistivity in the material, you get a process where it takes a lot of field strength to get the current density. And as you increase that resistive material, it takes less and less field strength to get higher and higher current densities. And the reason for that is that you're turning on more and more carbon nanotubes over a large area emitter. You're spreading it out so you can get more and more electrons out of the same carbon nanotube area. And in addition to that, as you increase the resistivity, you get more and more stable emitter. What that means is that you get the same current with the same field strength over a long period of time. And that means that you have a high current stable emitter based on that resistivity. The second physical property of the carbon nanotube is the structure of the material itself. This material, it has these resistive pathways in it, and it's a semiconductive material. And so that material has this weird amorphous shape, and that's actually intentional. This shape, you can see here kind of illustrated electrically, and here is a scanning electron microscope image of it. The material itself has multiple field enhancements. In other words, the material itself has multiple places where the electric field, instead of being a smooth surface where the electric field is even, the material itself bends the electric field. And as it bends the electric field, it creates, not at the carbon nanotube level, but at the material level, local hotspots in the electric field. And these local hotspots allow us to put a CNT emitter in those different local hotspots. You can see CNT emitters hanging off at these different hotspots. And that allows us to put more carbon nanotubes closer together. And it allows us to have kind of a redundancy of carbon nanotubes. If a carbon nanotube is emitting from here, it might be shielding one here. But if for some reason it burns out, the one further down is able to turn on. And so that allows us to have redundancy across the emitter so that we have more CNT emitters than we need to sustain the current, so that it can last over a long period of time if for some reason some of the individual carbon nanotubes burn out. And what that looks like is as we add more and more field enhancement features, again, we get higher and higher current density for the same turn on. But then if we look at driving that emitter over a long period of time, in this testing, as we drive the emitter, the voltage required to drive the emitter or the field stress required to drive the emitter goes up. And then when you get to 200 milliamps, it's going up steadily, but if you drop it back, it recovers very quickly and stops entirely. And the reason for this recovery, and you see it again on the side, that ability to recover is due to those redundancy in the emitters. Other emitters are able to turn on and the entire current is stable across the emitter. And using these properties, we can actually control how long the emitter will survive and how much current we get out of the emitter. If we want an emitter with very high current and very long lifetime, we can make a larger emitter. If we want an emitter with very high current and very short lifetime, we can make a small emitter. And if we want something in the middle, we can balance the size of the emitter. So by controlling the size of the emission area, we can control both the current and the life rather than just thinking about it as a current density issue alone. So what that means, so that's kind of a background of how we make electrons, but that's just a part of it. So these carbon nanotubes, these unique properties of carbon nanotubes create this large area emitter. And this large area emitter is put inside a vacuum tube to make X-rays. So we put the large area emitter in a cathode and then drive that cathode with a potential between the cathode and an anode to make X-rays. And that's once you have this electron current, the X-ray production is the same as any other X-ray production. You're accelerating free electrons in a vacuum through a potential into a heavy metal. And we typically use tungsten. So you're going to get a spectrum that looks exactly like any other X-ray. But because of the cold cathode, the carbon nanotube emitter, this tube has several unique properties. And these unique properties I'm going to go through step by step. So the first unique property of these carbon nanotube X-ray tubes is that they are electronically controlled. So if we go back to the beginning and we think about how typical X-rays are produced, you're running a current through a tungsten filament to generate thermionic emission. So there's a little bit of a lag in how precise you can control the current and when, as you ramp the anode voltage, you begin to generate electrons. Alternatively, for our tube, we actually turn on, well, first we turn on a focus voltage. The focus voltage simply controls the spot size electrostatically, and I'll get to that in a moment. And then we turn on the anode voltage. But when we turn on the anode voltage, the tube potential, there is absolutely no current in the tube, no dark current, there's zero current, no emission coming from the tube. And there's no emission until we turn on the carbon nanotube voltage. When we turn on the carbon nanotube voltage with a voltage of about 1,000 to 2,000 volts over those carbon nanotube array, you get current, and you get a current up to 200 milliamps for our tube. And that current makes X-rays. So because of that, we've got a very, very precise X-ray dose. It actually looks like a perfect rec function. So you can actually see here from a ray-safe measurement that the dose and the anode potential follow each other perfectly over the length of the pulse. And that gives us not just precise control of the dose and the dose through the entire pulse, but it also gives us the ability to turn on and off the X-ray tube very quickly, kind of like a grid control X-ray, only there's no wasted energy in this. So we've actually demonstrated in the lab that we can turn on and off our electron emitter up to about 500 megahertz, 2 nanosecond pulses, repeated, consistent pulses. And we only went that fast because we couldn't find a device to measure that. We had to use a multi-channel plate detector to validate that we were actually getting X-rays that fast. The second property that our tubes have is that we can very precisely and dynamically control the focal spot on the anode. So as I mentioned before, we have a focusing cup, but we change the voltage on that focusing cup to change the electrostatics to either consolidate the electron beam or spread out the electron beam from that large area emitter. So we take that large area emitter and we focus it into the anode. And so for our medical application, we focus it from 0.9 to 1.9. And in the digital X-ray imaging, the digital imaging application, the resolution of a digital imaging system is really determined by the detector. The source to detector distance is quite large, and the patient is on the detector, very close to the detector. So it's really the detector, not the focal spot, that determines the size, the image quality. And there was some interesting work done. There's a reference here where one of our mobile systems was compared to a conventional mobile system using the same detector, and the measured MTF was identical despite the difference in focal spot size. And that's because of the source to distance. So by changing the focal spot, we can take advantage of that to manage the heat in this application. However, the same physics, and we've demonstrated this, we could make a substantially smaller focal spot when the application calls for it. There's no fundamental limit that says it can only be a 0.9 focal spot. We could make a much smaller focal spot if the situation called for it. It's really a balance of the heat on the anode and the size of the focal spot we want and the current that we're running at. The other advantage of the carbon nanotubes is long life. So the emitter itself, as I talked about before, is very stable, and we can control the life of the emitter. The emitter itself degrades or changes very consistently depending on how hard you run it. So in these ones, we're kind of looking at life testing, not just of the emitter, but of the entire X-ray tube, and taking multiple exposures at different life. So the green and the orange are typical use, and the blue is the most aggressive use of that tube consistently. So as you can see, even with the most aggressive use of that tube, the tube is not likely to degrade in 5 years. But even if it did, and even if the emitter degrades, the dose and the focal spot remains consistent throughout that entire process. So when we do our life testing, we've actually looked at the dose and the focal spot consistently through the testing, and it doesn't change. And the reason it doesn't change is because you get the same current out of the emitter. The emitter itself is just, because of that redundancy, is using different carbon nanotubes at different times. So the voltage to drive it is increasing slightly. There's some point at which you run out of the voltage to drive it that you have in the system, and that's when it's considered at the end of life. But that is far beyond the typical use, and even in the most aggressive use, unlikely to happen. And that's validated both in the lab and in the field. But even as it degrades, you still get highly consistent imaging. And if it was to suddenly start degrading rapidly, even then it's not a binary ending. It's not like a filament that bursts. As the emitter begins to degrade, the voltage to drive it goes up, but it's going up steadily. It's not an instantaneous death because of all that built-in redundancy. So we're able to see when a tube is likely to die and be able to replace it, as opposed to just being an instantaneous death. So that long life and predictability is another advantage in the system. And then finally, overall, we leverage these to make a smaller and simpler tube. So as I mentioned before, we manage the heat by varying the focal spot. So that means that we don't use a rotating anode to get quite high current and dose out of a small X-ray tube. And the field emission is cold cathode, which means that there's no heat in the filament. What that means is the only heat in the system, and it is a lot of heat, is at the focal spot. But because the only heat is at the focal spot, we're able to draw that heat out and manage it differently. So it means that we don't need a glass insert tube in a big oil bath. So this image here, it is meant to really show the comparison between the entire tube assembly and the comparison in size. Because we don't have an oil bath, we're able to bring the X-ray shielding much closer to the tube. We use a EcoMass, which is a tungsten-filled polymer around the tube to make a smaller shielding. And we incorporate an aluminum window directly on the tube. So all of these things together allow us to make a very small, very lightweight, very high power X-ray tube. And then finally, we kind of think about the tubes differently. So based on these advantages of varying the focal spot, of electronically controlling of a simpler tube, rather than making X-ray tubes with a specific performance, we have identified applications where X-ray imaging is limited, or there are challenges in using the conventional X-ray imaging. And we develop custom X-ray tubes using these advantages for a specific solution, and then work to use that custom X-ray tube to design products that have specific workflow and features to meet the applications that have been identified. So it's kind of a different way of thinking about how you make an X-ray tube. Rather than just making an X-ray tube with a set performance, we kind of say, well, what does this application need as the performance? We make an X-ray tube for that, but then we think How can we make it smaller, lighter, fit into the human factors and workflow of the imaging system that we want to solve the problem that was identified? So to that end, we've developed 4 X-ray tubes to date as a company. Our first X-ray tube was 110 kV, went up to 80 MA on the anode, and half a second long pulses, and varied between 0.9 and 1.9 focal spot. The next tube is similar to the first tube, but it goes higher. It goes to 120 instead of 110, goes to 100 instead of 80, and goes to longer pulses. So the second tube covers a broader range of exposures for digital imaging. Then we have another version of the tube, completely different. So the first versions of the tubes are high voltage anode, and the emitter is referenced to ground potential. The next version of the tube is, or this version of the tube is negative potential. So it's at -160. It's a little bit lower current, but it's meant to run continuous pulses. And this is for security applications. And then we're working on what we call mini tube, which is a smaller version of the first tube. It's shrunk down even more. It's about the size of 2 golf balls in your hand. And that's for our stroke imaging system. And I'll get into that in a moment. This is just a brief picture of what it looks like to manufacture these X-ray tubes. We've got a facility with right in Tonsley, South Australia, in the city of Adelaide, where we have a clean room and a wet lab. Parts start in a wet lab where we make the emitter and we clean the parts. It goes into a clean room where we test the emitter and assemble the parts, and then to a tube manufacturing area where we bake the parts and test the parts to voltage. And if anyone would like more information about how we actually manufacture X-ray tubes, I'm very happy to talk to you offline about that. So what we do with those unique X-ray tubes is we make a collection of unique products. So I'm just going to get into each one of these products very briefly. And then again, like I said, I'm happy to discuss them in more detail offline. So the first product, and this is the one that's been in the field for over 3.5 years, is a mobile digital X-ray imaging system. So the first one we launched together with Carestream as the Carestream DRX Revolution Nano. We now have the Micro-X Rover and the Micro-X Rover Plus. The Rover Plus has the higher power X-ray tube in it. And really what we've done is we use that smaller, simpler X-ray tube to create a head that is only 6 kilograms in total. And that allows us to have a very flexible system. And so what it allowed us to do is engineer a system that was simpler and easier to use, more reliable, and didn't require any motors to move, but is still very simple and very easy to maneuver. It also allowed us to take advantage of lithium ferrous phosphate batteries to bring down the weight and simplify the batteries for a bedside imaging system. So that system has been used in a variety of applications. Most of those imaging systems are in hospitals, but they've also been used in home care. There's about 15 that we have sent to the Ukraine, where they are being used in field hospitals. And in field hospitals, they have the particular advantage of the lightweight and the size, but also the fact that they're fully battery operated. So in inserts and power, we're able to continue using them. There's even use in veterinary applications. And what this demonstrates is the reliability and the consistency of the X-ray tube. Thousands and thousands of X-rays have been taken with this technology over the last almost 4 years, and it's proved exceptionally reliable and stable in the field. And this is just some examples of the image quality that we get. We've gotten very positive feedback of the image quality. The image quality is largely determined by the detector and the quality of the digital detector and the software. We partner with a variety of detector suppliers, and for the rover, we work with other people's imaging software rather than our own, and other people's detectors, but we integrate it into our system directly. So the system acts as a fully integrated system. There's a screen on the system to review the images and set up the exposures, but it works with a variety of detectors, Carestream, Varix, Fuji, and are just a few of the detectors that we work with. We can really partner with anyone's digital imaging detector for this application. The next application is our portable stroke imaging. So this is work that we're doing as research right now. The concept is an array, rather than a single X-ray tube, using an array of small X-ray tubes, and that's that small two golf ball size X-ray tube in a static array. And this uses that property of the electronically controlled. So by switching which tube is on very quickly, we can take different cone beam X-rays on a large area detector. It's a curved large area detector of the head. And the application here is specifically trying to improve the clinical evaluation of a stroke. We're trying to identify very small hemorrhages in the brain. And the objective here is not just to see small hemorrhages in a brain, but to make a system that is lightweight and easy to use, something that can be directly integrated into any ambulance or medical aircraft, and that is cost effective, something that can actually be accessed by these different applications. This project is in collaboration with the Australian Stroke Alliance and the Royal Melbourne Hospital, with Flinders University, with Johns Hopkins University in the iStar lab, and with Monash University in the Health Co lab. So a lot of work together, bringing this together. And as you might imagine right away, people are thinking, well, how do you get full image quality out of this array? And so what we've done is, rather than have it be a completely static system, the system itself tilts slightly. And by tilting, so what it does is it takes all of the views and then indexes the whole system, and then takes another static array. And by doing that, we're actually able to get a full cone beam CT reconstruction of the brain. It's a sparse view CT reconstruction. The first work was done looking at model-based iterative reconstruction, and we were able to show in simulation that we could see very small bleeds. Additional work has been done and published, specifically looking at the scatter. So in this geometry, the detector is curved and the angles are not the typical cone beam 90-degree orthogonal angles. There's some interesting odd angles. So adjusting the scatter for that spatial variance and correcting it has been a huge amount of work done so that we can get an accurate cone beam CT reconstruction. And then finally, now looking at ongoing research to look at new imaging algorithms, diffusion-based synthesis to improve the reconstruction beyond a typical model-based reconstruction. How good can we get a few view cone beam CT to really pull out the small hemorrhages in the brain? And in this application, we're not really looking at full high quality CT as possible. What we're really trying to do is see how small of bleeds and how reliable of bleeds can we see. And pooled blood does show up quite well in a CT image. But this project, like our mobile X-ray imaging system, isn't just about the image quality, it's also about the usability. So we are doing a lot of work specifically with Monash University to investigate how do we design this head CT system, this head imaging system, to be easy to use, lightweight, collapsible, rugged and robust, able to fit into any ambulance and able to fit into any aircraft. And then also looking at how do we design it to be used such that an EMT can take a minimal amount of training and use it safely. How do we work with the local regulations so that you don't require a whole fit out to be able to take stroke imaging? Because specifically in Australia, the funding for this project, there's concern about rural Australia. There's concern about the parts of this world that are very far away from healthcare. How do we get high quality healthcare out to them? How do we work with people so that we can do early and quick diagnosis of stroke? So that's the work being done on use. The other projects that we're working on are in the security. So we're working on, we are bringing to market, and we have early prototypes of we call it an X-ray camera. It's specifically to help explosive ordnance detection. So it's people who go look for bombs to be able to image a suspect item from only one side using X-ray backscatter. And that uses a unique backscatter process where we take pinholes, multiple independent pinholes, and put them together to make one backscatter image to build up the dose. And this is different than a coated aperture because each of these pinholes is unique and don't overlap. And that allows us to recover the resolution, but also to increase the dose by overlapping them at a distance. And for this one, we actually designed a custom high voltage generator that makes a monoblock with our 160 kV tube. You can see how small that entire system is. That 160 kV tube and generator are in this with the detector, and this is the size of the system. The other work that we're doing is work in the airport. So current airports, the line getting through security is quite challenging. The solution is kind of like a conveyor belt. Everyone goes through sequentially. You're kind of slowed down by whoever's moving the slowest. So it limits passenger throughput. It also puts a huge workload on officers. It's quite invasive. There's lots of pat downs and looking through bags, and it's a fixed system. Wherever you go in the world, it looks relatively similar, and it's constrained by size. So we're working to reimagine using our technology what that could look like. Basically, instead of making it a long sequential system, making it a small modular system where the entire checkpoint is shrunk down into a little module, and those little modules are staggered in the same footprint with 7 or 8 of them in the same footprint as a conventional system. So you walk in, you load your bags into a little cabinet style system, you get scanned with body scanners, you collect your bags and you leave out the other side. So it's a constant flow modular system to kind of think about it like self-checkout at a grocery store. And this work is being done together with the Department of Homeland Security and TSA in the United States. And really the core of all of that is a smaller baggage screening system. And that's what we use our technology to do. So what we've done is we use 6 small X-ray tubes on a common high voltage assembly. So they're all connected to the same high voltage supply, and then using the electric properties of the carbon nanotube to turn on individual CNT emitters at a different time to make a smaller cone beam imaging system. And this is just some CT imaging of multiple bags imaged together in that system, in that development. And that's an ongoing work, as I said, funded by DHS and TSA. So in conclusion, we are relying on the fact that carbon nanotubes are near perfect field emission devices, but we scale the current using the unique properties of our bonding material that allow us to get high current out of the carbon nanotubes in a stable way. We use that to make unique X-ray tubes, and that builds into the unique products and imaging applications that we're working on. So thank you, and happy to answer questions.
Oh, thank you, Brian, for very amazing presentations. I think it really opens up new territory where we can go with the imaging technology, where we can minimize, reduce the size of the imaging technology and have it in an ambulance so that a patient with stroke can be triaged very efficiently. And by the time the ambulance comes to a hospital, the emergency staff already knows whether that person needs to be wheeled into the surgery or left for observation. So really quite amazing. I will read the questions, some of them that were presented in the Q&A session. Can I please ask, are these all prototypes? I know you have already released the X-ray tubes, or are there products, commercial products that are available for purchase at this stage?
So the mobile X-ray imaging system, the rover, this is products that are on sale today. We've got about between 300 and 350 in hospitals in about 20 different countries. You could buy one today from us directly or from our distributors or dealers. This is a commercially available product. The X-ray camera is in the first commercial prototypes and going to market as we speak. The stroke imaging system is still in the lab as a development project with Johns Hopkins and Monash and University of Melbourne. And the CT baggage system, we are building first prototypes and delivering them to TSA and DHS.
Okay, fantastic. You also mentioned that your X-ray tubes can sort of work with many detectors. So does that mean that you can also work with other manufacturers and they can use your X-ray tube within the existing equipment, or does it require lots of modification?
So as I said earlier, we've thought about X-ray tubes a little bit differently. We've made every X-ray tube custom to the application. So we can and do work with anyone who is willing and wants to work with us to get the most value out of the technology. It kind of has to be designed with the product in mind. If you simply retrofit existing technology, you don't get the same advantage. We are working with different people as we speak to how we can build new systems using our technology with either the same tubes or new tubes. And we are interested and willing to work with people who want to work with different components of the imaging system.
Yeah. There was a question about cost effectiveness. If you take into account that your tubes have long lifespan, and believe me, I used to work in a hospital and we had a case when we had to replace a tube on a CT scanner just about every 12 months. And each time it cost $100,000. What do you think? What is the cost effectiveness ratio of your product relative to standard X-ray based products?
In everything that we do, we want the entire imaging system to be accessible, and part of accessibility is cost effectiveness. So the current mobile X-ray system is quite cost effective compared to other digital X-ray imaging systems, and the X-ray tubes themselves right now are probably about on par with existing X-ray tubes for the cost. We're still making them in, relatively speaking, low volume. As we increase the volume, that cost will go down. The X-ray tubes are actually quite simple and the process is quite scalable. And in our medical imaging X-ray tubes, the ones that we have had in production in the field the most, we've got very, very high yield on those. So they're quite cost effective imaging tubes compared to conventional systems.
Mm-hmm. How long can the nanotubes be?
How physically long?
Yes. Or is there a reason that we need to discuss length?
No, the carbon nanotubes are typically between 1 and 2 microns in length and between 15 and 20 nanometers in width. Mm-hmm. So they are what's called few-walled carbon nanotubes. So there's a few layers of graphene rolled together.
And how do you put the carbon nanotubes where the matrix emitters hotspots are? I'm sort of reading the questions. Yes. I don't know whether that makes sense.
So the process of making the CNT emitter, it places them there. The actual process of how we do that is proprietary, but the process for creating both the structure and the location of the carbon nanotubes is to optimize that.
Mm-hmm. Have you published the X-ray spectra coming from your X-ray nanotubes? And how do you remove the soft component of X-rays? Do you use filtration?
So the X-ray tube itself has a 2.5 millimeter aluminum window, and we validate the spectra using a calibrated ray-safe detector, where at different anode potential we can look at the equivalent aluminum equivalents. Very, very early on, we actually measure the spectrum. The spectrum it's a conventional tungsten spectrum. We use tungsten anodes for the tubes that we are currently designing. There's nothing in the physics that say we couldn't use another. We could use a moly if we wanted to if we were going to mammography tube. There's nothing that says it has to be tungsten, but for the applications that we're using, tungsten is we believe is the best anode material, and you get a conventional tungsten spectrum from the tube.
People are asking, is it correct that the nanotube cannot withstand the forces in a rotating X-ray tube?
No, it can completely withstand the rotation. The only reason we don't do rotation is because everything we're trying to do is about simplicity and cost effectiveness. We manage the heat by altering the focal spot size for this application, and we can get quite high, up to 100 milliamp current using that. We don't currently use rotating anode. We could if we wanted to, and we've discussed that, but there isn't a need for it in the applications that we're looking at.
If you are looking at imaging maybe larger bodies, would you need to produce carbon nanotube products, X-ray tubes with larger currents? I think
we could.
when people were looking at the currents that you presented, whether they are sufficient.
So the medical tube that we have goes up to 100 milliamps right now at 120 kV, which is quite decent amount of dose. And given the effectiveness of current digital detectors, for everything that a mobile X-ray imaging system does, we believe that that's sufficient. There's nothing in the physics that precludes us going to higher current. It's really an optimization trade-off based on it. It's the anode heat, not the CNT emitter, that limits how much current that we can run off of that. If we went to shorter pulses, we could certainly go to higher current, but that doesn't really solve the challenge of very large patients.
What is the leakage outside the X-ray tube? Sort of, I presume it's all made to standards.
Yes, it's all made to standard. So the tube has we use a metal ceramic tube, so you get some attenuation just because of the stainless steel housing, and then we encapsulate that in an additional shielding. You can actually see it there. It's a tungsten filled polymer that allows us to make a molded shielding that's smaller and lighter. It's only smaller and lighter, not because it's less dense, but because it can be molded to the exact shape and optimized. So we meet standards in every one of our mobile imaging systems. As part of end-of-line testing, we do radiation leakage testing, of course.
Excellent. What is the field of view for your mobile digital X-ray?
It was designed to cover a 4343 detector at a standard distance. I don't know the full technical field of view off the top of my head. All of the technical data sheets are available on our website. If anyone would like, I will leave my my email address is here. If people would like follow-up questions for technical things that I can't recall off the top of my head specifically what the specific field of view is.
And I noticed that you also regularly publish the company, your research. You had a number of papers through your presentations. Are those papers available on your website as well if people want to do more scientific reading?
Some of them are, and you can get a hold of me. Some of the early papers are just papers in the field about carbon nanotubes and field emission. Carbon nanotubes have been extensively researched, and there's a huge body of work around how carbon nanotubes work. The papers that we've published or our partners have published, please get a hold of me. I'm happy to provide you with copies if necessary. Many of them are from Johns Hopkins, and those are available on the journal sites, but also we can make them available if people would like a copy.
Okay, can you maybe make a comment on the quality of the images? Are they, I know that's not just the X-ray tube, it's also the detector that determines, and reconstruction software. But, you know,
So there's a variety. So for our digital imaging system, the image quality is largely determined by the software and the exposure parameters. We've gotten very positive feedback across the board from our customers and from our partners about the image quality that we get, especially given the dose. We don't do our own imaging algorithms for our digital X-ray imaging. We partner with them, so depending on which software we're integrating with. For the head CT work, we are developing our own CT reconstruction, and we're working partnered with Johns Hopkins and the iStar lab to develop those algorithms, starting with the model-based penalized weighted least squares, but looking into more advanced diffusion and neural network-based approaches. For the backscatter imaging system, it's a unique reconstruction technique using the backscattered, and that's a lower image quality, but that's because it's X-ray backscatter. But you still get pretty high resolution from looking from backscatter. And for the CT, for the baggage scanning CT, again, it's our own internal iterative reconstruction technique that we're developing.
Now, regarding the stroke imaging systems in ambulances or on airplanes, how do you protect the paramedics or nurses or whoever is operating the equipment? Usually we have a CT scanner inside a shielded room, and the staff operate it from the outside.
There's two different ways. The first is the primary shielding is included in the individual tubes in the same way that we do with the mobile one. And so what that means is that all the primary beam is well shielded to only impact the detector. And so what we have to deal with is the scattered radiation. The scattered the total radiation dose is substantially less than a conventional CT. So this system will be substantially less than a normal head CT in total dose. So there's less scattered radiation and less total radiation. And the remaining radiation is primarily dealt with by distance, simply stepping outside of the ambulance. It's not intended that this would be taken as you are driving. It would be that you show up and you either take it right there, or you would go to a different location. With the aircraft, again, it's a simple and fast enough system that you would likely take it right as soon as you access the passenger. It's not meant that you would take it in flight, or you would take it as you're driving along. But the entire imaging process is only a few seconds. So you would, and it's meant, in both cases, the design is meant to work with, in this case, a Stryker patient bed, but working so that the patient wheels right into it, and you can, with simple adjustment, automatically take it. But so distance would be the primary way that you would shield
yourself. This is an interesting comment, and there are comments coming left, right, and center, so I have to close the discussion. It looks like your work is making X-ray imaging technology to become closer and closer to a consumer product. Something like the airport scanner, for example, is the first ever community-operated imaging device. How does this change in the users change the way you have to think about X-ray device design, especially in regards to radiation safety?
So first of all, we think a lot about the usability of the system and keeping it as simple and elegantly designed as possible. We think a lot about the safety and how do we build in safety features. And then we think a lot, and we're beginning to reach out and work with local regulators to understand where and how we work within those parameters. It would be nice if we could get to a place where it was truly community operated, as said, but we have to be, and we will always be sensitive to the local regulations and rules, both in terms of signage, buttons, dose, all of that is very important. When you think about the, you are right that it is kind of the passenger taking responsibility in the airport scenario, but it is still a very controlled scenario. In that one, the system is actually a completely enclosed lead box. So when the passenger hits it, there's no radiation coming out of it for them to be exposed, and they have no way of getting into it when it locks so that they can't get into it. But you are right, we are broadening it. The way that we do that is by ensuring that the system can only take specific exposures in specific settings to provide that protection.
Brian, thank you so much. Can I please kindly ask you to stop sharing your screen? Thank you. There are many more questions that I cannot get through, but you have presented your email address, and I can encourage everyone to contact you via email. And during the pre-meeting discussion, I also sounded Brian. It's likely that he will also attend the AAPM meeting, so people might have an opportunity to listen to more of your presentations and have an informal discussion face-to-face. I have to close the meeting today, but before I go, firstly, I would like to thank you, Brian, for a really exciting presentations on the new frontiers in technology for medical imaging. I would like to thank Professor John Damilakis for organizing the International Medical Physics Week. And of course, I would like to thank all the nearly 1,000 participants that have logged in to listen to your presentations.